Hey everybody, I wanted to take a moment to introduce you to the worksheet that you'll need to fill out and submit. And the purpose of this worksheet is to give you a little bit of exposure into enzyme kinetics. So on this worksheet, you're going to be asked a couple of questions about enzyme kinetics and basically putting together a graph. Now, I'll give you a little bit of a sketch for the graph that you should kind of expect to put together. But also I'm going to show you the worksheet itself. Okay, so the first thing that I'm going to do is share the worksheet. So this is it. This is your enzyme kinetics dry lab. Now I say this just because there's going to be a wet lab where you determine the kinetic parameters of your enzyme a little bit later on in the semester. But I decided to do this now so that you have a little bit of experience and you have the chance to kind of recall or ask questions about enzyme analysis. So this is the worksheet. As you can see, there's a data set. Everyone's going to be given that same data set. And so if you want to work in groups, that's fine. I have no problem with that. But I want you to put together your own work. And so what I mean by that is the graph that you put together, I'd like you to, everyone has to submit that graph. And then for your questions like what is KM? What is Vmax? I want you to put together your own answer for that. I don't want to see anything copied and pasted from ChatGPT or Google or anything like that. Try to articulate that in your own words. And so you might have to go back to your notes and look at that. Or if you have questions, feel free to ask me what those values are or what those things relate to. So what you're going to do is you're going to generate, looking at prompt number 3. Plot the data shown below using a Michaelis-Menten plot. Embed that plot in your completed document. Properly label your X and Y axis. Prompt number 4. From the data set shown above, generate the appropriate data or generate a Lineweaver-Burke plot and embed that plot in your data table. From the data, and then so then number 6 is based on the plot that you generated in question number 3. What is the approximate Km and Vmax of your enzyme? Number 7, based on what you did in plot number, or for your Lineweaver-Burke plot effectively, what is your Km and Vmax? And then are those Km and Vmaxes, number 8 is, are those Km and Vmaxes that you prepared from the 2 different graphs identical? Did you expect them or did you expect them to be, or are you surprised that they are not? And then number 9, the data set shown above does not show units for substrate concentration or initial velocity, but what are the acceptable units for these 2 values and what are acceptable values for Km and Vmax? Now, my spoiler there is there are more correct answers for these than there are incorrect answer options. So now I'm going to go ahead and switch over to the whiteboard and just give you a little bit of a reminder about the Lineweaver-Burke and Michaelis-Menten plots. So the Lineweaver-Burke plot is also known as your double reciprocal plot. And that's the one that people always like to see whenever they're doing inhibition studies. And so it's pretty easy with a Lineweaver-Burke plot to determine what type of inhibitor that you're working with if you're doing inhibition studies. Now, this graph or this data set that you're working with, the first thing that I want to do is go ahead and put together my Michaelis-Menten plot. So the Michaelis-Menten plot has a y-axis and an x-axis, where your y-axis is your v sub 0 or your initial velocity. Your x-axis, on the other hand, is substrate concentration. Now, it's pretty reasonable to expect that a Michaelis-Menten plot will look a little bit like this, where each one of these points, you have a basically correlating your x and y axis as your substrate concentration in successive trials increases. So if we look at your data table, when your substrate concentration is 0.05 and your initial velocity is 263.157. Okay, that's worth noting. Then when you increase your substrate concentration, your maximum velocity, or your initial velocity, goes up. So as we're increasing our substrate concentration, our initial velocity goes up. It continues to go up as we continue to increase our substrate concentration. At some point, however, the amount of substrate that you add, well, your velocity is not going to be changing very much, if at all. And so that's one of the things that you're kind of confronted with when you're making a Lineweaver-Burke plot. You see this sort of plateau effect. No matter, or as you add more and more substrate, the velocity, the initial velocity does not change. Okay. Now, as we proceed from there and come up with the other plot is a Lineweaver-Burke plot. And so to put together a Lineweaver-Burke plot, which is also known as a double reciprocal plot, all of the values that you have for your y-axis and for your x-axis, all that you're going to do is you're going to take the reciprocal of those. So your y-axis is going to be labeled 1 over initial velocity, and your x-axis is going to be 1 over substrate concentration. So whatever values you have for your substrate concentration, for example, 0.05. All that you're going to do is say 1 over 0.05, which you can plug that in and figure out that that is 20. That is going to be this point. Then you'll take the corresponding velocity, initial velocity, and say 1 over, I think it was like 263.5 or something like that. And you'll plot that. And what you're ultimately going to see is a plot that looks a little bit more like this. It's a linear plot. So the data that you represent is going to be linear as opposed to, well, what you see up here, which is a hyperbolic curve. So you need to come up with these two values. Now, these two graphs, once you have these two graphs, you'll be able to figure out the Km and the Vmax. For a Michaelis-Menten curve, your Vmax is effectively right here. The maximum velocity, where your data plateaus, where you add more and more substrate and the maximum velocity, or the velocities, does not increase. And that's kind of a number that you can just kind of deduce. Then the other value is your Km, which your Km is you take your maximum velocity and you basically cut it into, say, half of Vmax. And then you draw a line and come up with the concentration that gets your enzyme to go at half of the maximum velocity. This is your Km. So those are your values for a Michaelis-Menten plot, or an MM plot. Whereas the double reciprocal plot, it's going to be a little bit different. For example, this x-intercept is going to be negative x is equal to negative 1 over Km. Then this y-intercept is going to be 1 over Vmax. So you need to figure out when your line intersects through that upright, or through those axes, what is that value? And what is the Km and what is the Vmax based on those? Now, a good way to figure this out is, well, you're going to get a line, y equals mx plus b. If you want to figure out what this is right here, you're going to set x equal to 0. And then if you want to figure out what this is right here, you're going to set y equals to 0. So manipulate this equation accordingly to figure out what is my x-intercept and what is my y-intercept. Put those graphs together, come up with a Km and your Vmax, make a presumption as to, or kind of analyze the data points that you got. Are they similar? Are they different? And go from there. All right, well, I hope this was helpful and hope you have a good one.